This is a video presentation of Chapter 1, Section 3, entitled Scientific Notation. Our objective here is to be able to multiply by powers of 10 and express numbers in scientific notation. So it's a good place to start here by talking about the definition of scientific notation. What is scientific notation? That's a kind of shorthand that can be used to write large numbers. Now when we're talking about large here, we're talking about their actual length. All right? Then generally here when we talk about scientific notation, we talk about things that involve decimals. So we mean a number that has a lot of values after the decimal point. It doesn't mean large in terms of number line large. It could also be a very, very small number, something that's very close to 0, but has a lot of values after the decimal. That's when scientific notation comes into play. Based on the name, you guessed when you're going to use this a lot is in a science type of situation where they have those types of very large numbers and very small numbers. You don't want to be writing out those very long numbers, whether they're small or large in terms of the number line. What you want to do is express them in the simplest way you can, and that's where scientific notation comes into play. So when we're talking about the distance perhaps from Earth to some celestial object, which could be many light years away, and if, let's say we wanted to measure in feet, would probably be a very large number. There's a smaller way to express that same value. That's going to be something we would do in scientific notation. The same thing would be true if I was trying to measure the size of a microscopic particle. Something that's very, very, very small might measure out in something that has a lot of values after the decimal. And there's another case in which we would end up using scientific notation to express that value, as opposed to writing something that has perhaps 100 numbers after the decimal. So, in the first question, they're asking us to multiply 14 times 10 to the third. Now, this gives us some ideas of the concepts of scientific notation, but truth be told, this question is not true scientific notation, and you'll see why in a minute. But let's go ahead and take a look here at evaluating this as they've asked us to do. Now, there's a couple different ways you can proceed with this. 10 to the third power, as we know from our study of powers, can be written in a different way. 10 to the third power is the same as 10 times 10 times 10. In other words, we use 10 as a factor 3 times. So this is really the same as 14 times 10 times 10 times 10. Or 14 times 1,000, which is what 10 times 10 times 10 simplifies as. So if I do 14 times 1,000, that's 14,000. Now, the nice thing is, when you have something written as in with a base of 10 and whatever exponent, that is the setup for scientific notation. And when that exists, this exponent, all it really tells you then is how many times you move the decimal out. In this case, to the right. So here with this exact same problem, instead of us figuring it out with multiplication, what we do is we just take and kick the decimal out 3 times to the right based on the fact that that exponent here says 3. So in 14, I'm moving the decimal 3 times to the right, which is what they're showing you right here. And as you can see, that changes into 14,000. It matches our answer that we had above, which it logically should, but it's obviously a lot less work and a lot less writing. Now what they're asking us to do in example 2 is they're asking us to kind of go the other way. They're asking us to take a value and write it in scientific notation. Now we already know from what we saw in our last example and what we heard in our last example that scientific notation always involves a power whose base is 10. And as you can see, that's part of the answer that you see there. But what that doesn't explain is where this comes from. What you want to do is take your number and insert a decimal such that the value becomes something between 1 and 10. So if I'm looking at 4,340,000, if I put the decimal between the front 4 and the 3, where I've just drawn that red X, that then is 4.340000. 4.34 is indeed between 1 and 10, which is what's required of scientific notation. And that's where this front part of the answer came from. That's me sticking the decimal in and writing it as something that's between 1 and 10. Once you have that, again, it's always times 10 because you have to have a power that involves a base of 10. And then we have to figure out the exponent. Well, the exponent is the number of times I move the decimal to make the decimal land between that first 4 and the 3. The decimal, when it began, was out here after the last 0. Of course, it's not visible, but that's where it would be if I added on a decimal and some zeros. So to move the decimal there, I moved 1, 2, 3, 4, 5, 6 jumps to the left. And hence, the exponent that matches the base 10 is a 6. And that's always how that generates. Now, this leads to a discussion back to example 1 when I said it wasn't true scientific notation. If we go back for just a moment and look again at example 1 here, notice that this first number here is 14. Well, remember, I just said that to be true scientific notation, it has to be something that's between 1 and 10. And of course, 14 is not between 1 and 10. However, the work that we did is still what we would have done with the rest of scientific notation, in that that exponent is 3. We move that decimal 3 times out. Now, this probably also leads to another good discussion. How do we do a small version of a number? Something that's very, very close to 0. Let's say it was something like 0.000007. Well, the decimal in this case would have to move the opposite direction to create something that's between 1 and 10. It's moving 1, 2, 3, 4, 5, 6 jumps off to the right. I'm sorry, 7 jumps off to the right. When we move to the right, well, you should be able to figure out what's going to happen here. When we move to the left, the exponent was positive. So when we move to the right, the exponent all of a sudden becomes negative. So this is now 7, which is acceptable because, remember, it has to be something that's between 1 and 10. It's always times 10. And then the exponent is how many times I moved it to the right, 7. But again, because I'm moving to the right, it's now negative. So this is 7 times 10 to the negative 7. We can then work this same idea backwards. Let's say I gave you 2 times 10 to the negative 3rd and ask you to write out its value. Well, the negative 3 indicates that the decimal is going to have to go back that way. Remember, this is something that's very, very close to 0. So I'm going to take my decimal and move it 3 times off to the left. And as you can see, those empty jumps, of course, as they always do in any situation with place values where we have any type of empty jump, fills in with a 0. So this is the equivalent of 0.0002. If you can remember that negatives generate those things close to 0, and that those positives are going to generate very large numbers that are much further away from 0, probably very far off to the right on the number line, you probably have a good understanding of what's going to happen here. And you won't necessarily have to remember certain rules for everything because you'll just see it based on those concepts. The population of China in the year 2000 was estimated to be about 1.262 times 10 to the 9th. Write this number in standard form. So, this one is in proper scientific notation. Remember, what's in front here has to be something that's between 1 and 10. And this is indeed between 1 and 10. Now, remember, we could get the calculator out and multiply, but that's probably going to be more work. Just look at the power. 10 to the 9. With the exponent being 9, 9 is going to force us to kick the decimal towards the right 9 times. So as you can see here on this illustration, they're moving the decimal 9 times off towards the right. They filled in a bunch of empty jumps here off the end with zeros. And as you can see, once we do that, the number that's generated is 1,262,000,000. In other words, the population of China was about 1,262,000,000 people in the year 2000. Number 4. In 2005, the population of Mexico was 1.06 times 10 to the 8th, and the population of Brazil was 1.86 times 10 to the 8th. In which country do more people live? So now what we're doing is we're comparing numbers written in scientific notation. Now that first paragraph describes comparing the numbers in scientific notation. When we have numbers written in proper scientific notation, what we want to do first is compare the exponents. Remember, the exponent is going to generate how many places are after the decimal. So if I have to move something 8 times to the right versus something 9 times to the right, we know that when I move that one 9 times to the right, it's going to make a number that's 1 digit longer. Again, the caveat being that it's got to be written in proper scientific notation. So if the number is longer, it has to be bigger. So automatically we would be done. Now, when the exponents are the same, we compare the number portion of that scientific notation statement. So in this question, we would be talking about the 106 and the 186. If the exponents are equal, then we look at those. And whichever one is bigger is automatically the larger number then. But again, that's only when the exponents are the same. Well, for us, this question is a good example of that because the exponents for the Mexico number and the Brazil number are both 8. So we can't do any comparisons there. So what we have to look at here when we compare these in scientific notation is the numerical part, the 1.06 and the 1.86. Since 1.86 is bigger, the Brazil number has to be bigger. Now notice the way they're comparing them, they've put the 1.06 first. So we're going to say that 1.06 is less than 1.86, or in other words, 1.06 times 10 to the 8th is less than 1.86 times 10 to the 8th. Or in other words, more people live in Brazil. If you want to vet this out, you can change these into regular numbers. Remember, both, since the exponent is 8, that means you're going to move the decimal 8 times off towards the right. All right, in this case, it's going to generate 6 empty jumps. Same thing with the Brazil number, 8 times to the right. Again, filling in the empty jumps with zeros. Well, as you can see, what we have here then is a comparison of 186 million and 106 million. Well, no surprise to us, 186 million is bigger than 106 million. So with the Brazil number being larger than the Mexico number, it vets out exactly what we said here based on just looking at these numbers in front when the exponents are the same. And again, further proof that more people live in Brazil. So now what they're asking us to do in the check it out examples is some practice of what we've just seen. In the first question, we're going to multiply 12 times 10 to the second. Now, before we start question 1, what do we know about question number 1? What we know about question number 1 is that it's not written in proper scientific notation. This number in front has to be between 1 and 10 in order to be proper scientific notation. So it would actually have to be 1.2 if we were talking about proper scientific notation. But the rules of scientific notation we can still apply to this question. We look at the power and it says 10 to the second. Since the exponent is 2, we're going to kick the decimal 2 times to the right here. So in 12, move the decimal 2 times to the right, and that's 1200, which is what you see illustrated on the screen. Then we're going to write 8,421,000 in proper scientific notation. So remember, what you want to do to start here is insert the decimal such that it becomes something that's between 1 and 10. So I put it between the 8 and the 4, which would be 8.421000. Now, of course, zeros at the end of a decimal don't matter, as you already know, so they get dropped off, and it's just 8.421. Remember, it's always then times 10 to the something, and we have to figure out what the exponent is. The exponent is simply based on how many times we move the decimal to generate that 8.421. So I move the decimal 1, 2, 3, 4, 5, 6 times in, so the exponent becomes a 6, and that's my final answer. 8.421 times 10 to the 6. One last thing. As far as the power goes, the base is always going to be 10 in scientific notation for a couple different reasons. But the primary one being is that our numbering system is a base 10 numbering system. Base 10 means that all the place values revolve around 10. Right? Think about our place values after the decimal. Tenths. Well, we know about that. That says 10. Then we have hundredths. Well, that's a 10 times a 10. And then we have thousandths. Well, that's 10 times 10 times 10. And then we have hundred thousandths. 10 times 10 times 10 times 10. That's what we mean when we talk about a base 10 numbering system, is our place values revolve around the number 10. You can't do a 9 there because it won't have the same result. All right, because 9 wouldn't account for the place values we use in our numbering system. So again, make sure that that base here is always 10. It must always be. The exponents can be different, but the base is always 10.